Hello and welcome! In modern biology, we can generate these just absolutely massive mountains of genetic data. But here's the crazy part. What if almost all of that data, like 99% of it, is just noise? Well, today we're going to dig into how scientists find that tiny, crucial signal, the 1% that could actually lead to the next huge breakthrough.
This is a story that plays out in labs all over the world. A researcher runs the perfect experiment, but the result isn't some clear, beautiful answer. Nope, it's a jumbled, messy pile of raw data. The challenge isn't over. It's just moved from the lab bench to the computer.
So here's a way to think about it. Imagine you're in a super loud, crowded room, and you're trying to listen to just one person's conversation. The voice you want to hear, that's the real biological signal. It's in there, but it's getting totally drowned out by all the background chatter. That chatter, that's what we call technical noise. And it's just an unavoidable part of these big, high-tech experiments like microarrays that measure thousands of genes all at once. And this noise, it doesn't come from someone making a big mistake. Oh no. It's the buildup of all these tiny, unavoidable little variations. A slight change in the room's temperature, a different batch of chemicals, or hey, even just a different person running the experiment that day. Each one of these things adds its own little layer of bias that, when you pile them all up, can completely hide the real results. Okay, so how in the world do we fix this mess? Well, that's where data preprocessing comes in. It is the absolutely essential first step. So if our raw data is that noisy room, preprocessing is like putting on a pair of amazing, high-tech noise-canceling headphones. The whole goal is to filter out all that technical chatter, get the data lined up, and let that true biological signal finally shine through. To really see how this works, we're going to stage a little competition. You could call it a data science bake-off. We're taking 5 of the most common preprocessing algorithms for a really popular technology called the Affymetrix platform, and we're going to put them to the test. All right, let's meet our players. First up, we've got MAS 5.0, the original method right from the manufacturer. Then there's RMA, which is widely known as the gold standard in the field. We've also got GCRMA, a pretty clever version of RMA that pulls in genetic sequence data. PLIER is another contender from the manufacturer with a different strategy. And finally, there's VSN, which is all about stabilizing the data's variability. So who's going to come out on top? Let's find out. Now, to find our winner, we're not just going to take their word for it. We're running all 5 of these contenders through a really tough 3-part quality control gauntlet. Let the games begin. First up, the alignment test. Now, the whole point of preprocessing is to get rid of those technical differences between samples, right? So after a good cleanup, all of our different data samples should look, statistically similar. Their distribution should be all nice and lined up. So how do we check this? We use a really powerful visual tool, the box plot. Each one of these boxes you see represents the full range of data from a single sample. What we're looking for is consistency. If an algorithm did its job right, all the boxes should be lined up at about the same level. That tells us the technical junk has been successfully removed. And the results for round 1 are in. MAS 5.0, it really struggled. It just didn't align the data well at all. PLIER did a little better, but it created some weird negative values that can really mess up your analysis later on. But look at this. RMA, GCRMA, and VSN absolutely passed this test with flying colors. Great start for them. All right, on to our second challenge, the stability test. Here, we're checking for a whole different kind of bias. Ideally, the amount of noise, or variability, in the data shouldn't depend on how strong the signal is. We want that variability to be consistent, whether the signal is faint or loud. The tool for this job is called a mean SD plot. It basically plots the signal intensity against its variability. Now, what we want to see is a nice, flat red line going straight across. That flat line is our hero. It means the variance is stable and doesn't care how strong the signal is. Any kind of slope or curve, that's a big red flag. And would you look at that, the results are crystal clear once again. Both MAS 5.0 and PLIER show this really strong, undesirable trend. Their variability is all over the place, depending on the signal intensity. But our other 3 contenders, RMA, GCRMA, and VSN, they just performed beautifully. Much, much more stable variance all the way across. Okay, this is it, our final decisive test, this similarity test. Here's the logic. If we've successfully removed all that random technical noise, what should be left is just the pure underlying biology.
And since these samples are what we call technical replicates, we expect them to be extremely similar to each other.
So we measure this similarity using a statistic called Pearson correlation. It basically gives us a score between -1 and +1. A score of 1 means the samples are perfectly identical. So for this final test, it's simple. The higher the score, the better the algorithm did its job of taking out the trash.
The gauntlet is complete. The tests have been run. It is time to tally up the scores and finally crown our winner. And the final verdict is in. MAS 5.0 and PLIER, well, they really struggled in our tests, and their use is generally not recommended. But RMA, GCRMA, and VSN were absolute star performers across the board. They got good alignment, good stability, and excellent similarity. They are the undeniable winners of our bake-off. And hey, this conclusion isn't just our opinion from this one bake-off. It's backed up by years and years of research. This quote from our source material says it all. RMA, in particular, has really earned its title as the gold standard because it's just so robust and reliable.
Now, while we focused on one specific platform, Affymetrix, the lessons we learned here are universal. This need for tough preprocessing and quality control isn't unique to one technology. It's a fundamental principle of good data science, period.
For example, just take a look at the workflow for Illumina, which is another huge microarray platform. The names of the steps might be a little different, but the logic is exactly the same. First, you correct for background noise. Then, you aggregate your data. And finally, you normalize it to make sure all your samples are comparable. See? It's the same core philosophy. And what's really interesting is that even tiny choices within a workflow can make a big difference. On that Illumina platform, for instance, just choosing a more robust method for one of the steps, data aggregation, can improve your accuracy by up to 5%. Now, that might not sound like a lot, but in genetic research, that could be the difference between chasing a false lead and making a real discovery. It just proves that constantly testing and improving our methods is key. So you see, choosing the right pre-processing method isn't just some boring technical detail. It's the very foundation of reliable and reproducible science. And as our data gets bigger and way more complex, the methods we use to find that signal in the noise are only going to become more and more critical. Which leaves us with one final question to think about. What's going to be the next gold standard?